So we're going to try and find the slope of the tangent line of that graph right there at square root of 2 comma negative 1/2. Slope of the tangent line, what does that lead you towards? Do what? Derivative. This particular one could be done either way, because is solving that one for y all that difficult? Not really, but is implicit all that difficult either? Not really. Now that you've done it a couple times, it's not that bad, right? So seeing we're working on implicit, let's go ahead and do it. Derivative of that is 2x, and again, you're going to stop writing this, but I'm going to keep writing it for you. Dx, right? Plus 8y dy dx equals, now you do have to take the derivative of 4, and it is 0. And as it was asked before, remember, other stuff can be over there, and then you just take the derivative of that the same way. But right now, it's been constants a lot, which is why it always equals 0. And so the one thing we can get rid of right away is that, because dx is just 1. Okay? And so well, what do you do now? Well, we want to get dy dx by itself, because I want to know the slope, right? But there's only one dy dx, which is better than some of the ones we had yesterday, right, where we had to factor stuff out. There's no factoring here. Well, the dy dx is already kind of right there, and so let's get this out of here. Right, so then these cancel. So 8y dy dx equals negative 2x. And it's almost by itself. We almost have the derivative. Divided by 8y. And those are gone. And so my derivative. And now I told you yesterday, if you know you're putting a point in, you don't necessarily have to simplify, but that's a pretty easy simplification right there, right? I mean, we can probably do it in our heads, I hope. It'd be negative x over 4y, right? The 2 comes out of each of them. So that's the derivative. And the funny thing is why do we take the derivative? Because it doesn't even ask for it. It doesn't say take the derivative. But really, that's how we find that. And so translated, that's what it says, find the derivative. And now, where this x is, I'm going to replace it with the x value, right? And this y happens to be on the bottom, so I'm going to replace it with the y value. Okay? And that will tell me the slope. So, negative square root of 2 over a negative, right? Because if I put a negative half in there, negative 2. So in other words, negative square root of 2, it really ends up just being positive. Yes? Well, let's wait till, is everybody done with this one so I can do the question? Everybody's got it? The question was, what if it's negative 2/3? Well, then we would put negative 2/3 right here. I would figure out that's negative 8/3. So it's actually the 3 that would get flipped up. See that? So the negative 8 would stay down, the 3 would get flipped to the top. Okay. Or you could just start using your calculator and figure out, what does that end up being. Either way. Did that answer your question? Or no? Okay. And it's not because I had to make sure this point actually occurs where? That actually has to occur on that graph somewhere. Okay, so I actually went through and found out that that's actually one of the points. Again, that was somebody asked, what if it was negative 2/3? How would you do it? And very good question, actually. Because let's face it, they don't always come out to like 4 times a half or something like that. Mm-hmm. So that was just kind of a review of what we did yesterday. Yeah, looks pretty good. What's this asking me to do? Almost. Second derivative. Which is saying find the derivative and then find it again. And I'll be very honest, this would be quite a bit easier if we did it explicit. But I chose this particular one because this is kind of an easier one, second derivative. Okay. This can get kind of complicated. Okay. To solve this for y, you would subtract the x squared and take the square root. right? That's how you would do that. But here, y double prime. So we better start with the first derivative. That sounds like a pretty good idea, right? Now, I'll give you a little, well, we'll just see what you want to do. Now, here we go. Implicit. 2x dx dx plus 2y dy dx equals, once again, there's that constant. Okay, it is very common to have a constant. Right, well, this doesn't. I said this is supposed to be hard, right? This doesn't look hard. We're not anywhere yet. That goes there. This is pretty simple. So then we're going to subtract. This is almost the same thing we did in the last one, right? Subtract 2x. So 2y dy dx equals 2x. Yeah, I can keep the same color. Divide by 2y. So my first derivative is really just negative x over y. Agreed? Well, that didn't seem very difficult. Yes? That's where we're going to, and that's the question was, how do you write the second derivative notation? And it's a great question. And that's where we're going to go next, and I'm going to see which way you want to proceed. Second derivative, I'll just write the notation up there quickly. It's take the derivative twice of y with respect to x twice. See that? Isn't that what we're doing? Taking the derivative twice of y with respect to x twice. That's the notation for second derivatives. You see it gets a little ugly? And so that's where some people, when they have this particular type of problem, they say, you know what, I'm good at this implicit stuff. And they rewrite dy dx as just y prime. As long as you know that's what dy dx is, it kind of, then you just write y double prime. And it's a lot neater. And it's completely up to you how you want to proceed. It doesn't matter to me, really. It's just some people don't like to have to write that. And that's what I was going to say earlier, but then I decided to wait till now. So either we can erase this dy dx and replace it with y prime, because it's the same thing, or we can deal with it that way. Your choice. Y prime, all right. I can always show you what it would look like if you went the other route. So the change is you have decided to go y prime. Good choice. All right. Now let's not forget that, and it's a very easy thing to forget, is that I have to take the derivative of that y prime. And what is the derivative of y prime? It's easier than you think. Y double prime. Yeah, it's easier than you think. Y prime prime. All right. So we took the derivative of that right there. So equals. The nice thing is isn't it almost explicit at this point? It kind of is, isn't it? But there's a y in there. So it's kind of implicit and explicit at the same time. It's very strange. And so how are we going to take the derivative of that thing? It seems so simple, so innocent. Negative x over y. It unfortunately has to be quotient rule is probably your best bet, to be honest with you. Or we do have another option. We can rewrite it as that and do product rule, right? You tell me. This is your problem. I can do it either way. Product or quotient? Quotient. Let's do it. So quotient says, it's good. We haven't done this in a while, so it's probably good that we do quotient. Quotient says to take bottom, and bottom is just y. Did I take the derivative of y right there? No, I just wrote it down. So do I put a dy dx on that? Nope. So y times the derivative of the, so we're not doing this one, right? I better X that out so I don't look at it. Derivative of the top, which is? Yep, if you wanted dx dx, right? Very good. I wasn't going to write that. See, I'm so much in the habit of not writing that sometimes it's hard for me to do. No, you never really have to write dx. I just write it so that you can see that we don't forget. It's basically so we don't forget the main one that we really need to write, which is dy dx. Or you can write it as y prime if you want. Now, what's next to be written? This is the one thing we haven't done in a while. Minus, very good. Y minus. That's quotient rule. It says to subtract. And we did what? Bottom derivative of the top. So now, top, and let's do that so we don't mess up, right? Top, derivative of the bottom, which is kind of like 1 dy dx. Or again, you can write y prime there if you want. All over bottom squared. We are doing fantastic. That was being serious. That wasn't. Let's clean this thing up. Look at it this way. We don't have any negative exponents, right? Would we have had some negative exponents doing it product rule? Yeah, so is quotient maybe a good idea this time? How about this? And can I take negative 1 times y? Oh, what is that? Minus a negative, so in other words, plus. We can do better. It's not bad. But here's the point that we can do better, and I think it goes back to what somebody was saying. I'm not sure if this is what they meant or not. I can replace something in that derivative. Yes? Yeah, do I know what dy dx is? That's the first derivative, right? Do I know what that is? What is it? Negative x over y. Okay. Right, in this problem, the derivative of y with respect to x we already had done. We already found what that was. So now let's just clean it up. Do you agree this ends up minus then? Minus x squared over y, which is also over y squared. We're actually going to clean it up some more. Because I just want you to see that it can be done. That just looks weird, doesn't it? There's like a term and then a fraction, and it's all part of a fraction, and it's just weird. What do we normally do when we have something like that? What's that? Yeah, it could, but then this first negative y doesn't have a y in the bottom. It has a 1 on the bottom, but you'd have to have it, this y right there that I'm pointing to right now, that people listening to the recording can't tell what I'm pointing at. That y right there is only underneath there, and it's not underneath there. So you can't just throw it on the bottom. Oh, common denominator might be a good idea. There was no avoiding the common denominator thing, so don't feel bad. All right. All right, we're just going to write it over here then. So I basically have to multiply the bottom by y, but then you also have to multiply the top. Why do you have to multiply both? Yeah, I'm multiplying by 1, and you can multiply anything by 1 at any time that you want. So to agree, this basically becomes negative y squared minus x squared all over y, which is then all over y squared. Now can that y go down and join y squared? It actually can. For those that don't want to look at it that way, I could write this over 1 and flip it, right? So, or you could say the y squared is joining the y. Either way, right? They're coming together. And just so you know, the calculus on this problem has been done for a long time. So it's negative y squared minus x squared all over, very good, y cubed. You get that far, I am going to be supremely happy. You can simplify it more, I'll be supremely impressed. So why don't you take a second now and see if you can go one step further. Because you actually can. It can get one step better. But if you can't, it's okay. Okay, so the mic's been off for a little bit there to see if anybody could simplify it any further. The one question that came up a lot is where did the negative y squared come from? And that's right here because we needed the common denominator of y, and so we multiplied the top by y, and negative y times y is negative y squared. Anybody got anything? How about if I get you a step closer? And let's erase this because I'm just running out of room. And plus, this may help. What I chose to erase may help. Do you agree that I could do this? I wrote it that way on purpose, and I wrote it where I wrote it on purpose to lead you towards what you can actually do. X squared plus y squared in this problem has to equal 16, correct? Do I have x squared plus y squared right there? Can I replace it? Sure. It happens surprisingly a lot. I wouldn't necessarily go that far, but did you see how it was very similar to kind of what we did over here at the beginning when we had that extra credit problem. Very similar. We used the original to change it a little bit. I wouldn't go as far as to saying if that happens, you know you did it right, though. I wouldn't quite go that far. That's a tough problem. I will not give you any that are much harder than that. Because, of course, if we had done this one explicitly, we would have been done a long time ago. Okay? But I want you to work on your implicit. That's an excellent example. I have one right here. Example 3 on my notes. So if I have one written right here, that tells you how good of a suggestion that was. And so on your back of your sheet, that is, so there we go. I'll just kind of tell you the directions here. There's your function. I would like you to find the slope of the tangent line at that point. And trust me, yes, that point is actually on that particular graph. So your original is right there, and I wrote it down about a foot for some apparent reason. I don't really know why. But this one does not take anywhere as near as long because am I asking you for a second derivative? How do you know I'm not asking you for a second derivative? Well, I would have said y double prime or something like that, or I would have said something else that you'll learn later. But I asked for the slope of the tangent line, which comes from the first derivative. The second derivative tells you something else. I know what I would do right away, because anybody want to solve for y and have some arc cosines in this thing? That's the only way I'm getting cosine away from y. And so that's probably a bad idea, seeing you don't know the derivative of arc cosine. So we probably better not do that. Yes, it does actually have a derivative. All right. So we're going to do it implicit. Any suggestions to start with? I know what I would do. Not too bad, actually. The derivative of sine and cosine is not really a big problem here. What was that? I would divide by 2, because haven't we done a lot of them that had a constant over there? And what always happens to that constant? It goes to 0. So why don't we just put as much over there as we can as a constant? So that's what I would do. Yeah, let's divide by 2. It's just going to save me from having so much junk in my derivative. Well, you know, that's good. So what's the operation that's right about there? Uh-oh. Product rule. So write down the first one. Okay, the first one is times the derivative of the other one, right? Negative sine, very good. Of y, you got to write it down, right? And then you have to take the derivative of the angle, which is dy dx. That's Trigg's chain rule, remember? Yep, plus y plus. Yeah, it's in product rule, right? That's what's in there. So now we have to flip it around. So write the second one. Do I write dy dx again? No. Times the derivative of the first, which is of x. And really, you do have to take the derivative of that angle too, but how come I never really had you worry about that before? What's the derivative of x? It's just 1, so I haven't had you really worry about it. See, all these things that I've saved you from, all divided by something or what? Oh, equals though, and we were very clever with our move there. Now it just equals 0. Do you have to divide by that too? No. But it just saves you dealing with a 2 all the way through this thing. Yeah. All right. What do we do now? You did a great job of product rule, but yeah, you got to clean it up. And when you say clean it up, you mean do what, basically? Okay, well, what's our main goal here? Get dy dx by itself. And let's face it, we're getting really good at doing this. I'm going to go away. And so right here, we have basically, if I look at this first term, I have a negative sine of x, sine of y. Unfortunately, you can't make that sine squared of xy or something like that because the angles are different. One is x and one is y, so you can't put it to sine squared. And then plus cosine of, and you can write it in either order, cosine of y, cosine of x, and it would help if I wrote the dy dx in there. So I'm just going to make my y really, really tiny and then fit in a dy dx. Sorry. That was me just messing up, not seeing if you were paying attention, but just me messing up. Equals 0. So sorry if that has caused any pain for you. Did it? Extreme pain? Yeah, I'm sorry. Yeah, get those cosines out of here because they don't have a dy dx on them. Get them out of here. So just subtract them. From both sides, of course. Making them cancel. So we got negative sine of x, sine of y, dy dx equals negative cosine of y, cosine of x. Yeah, get that dy dx, so get this stuff out of here, divide by all that stuff. On both sides, once again, of course. Whoops, that looks like a x. There we go. Gone, gone. There's your derivative. Well, let's take the negatives. You could. This is all multiplication on top, right? All multiplication on the bottom. And so the negatives can cancel, right? Like that. So that's your derivative agreed. So now if I had any x or y values, I could substitute them in. And we do. Pi over 4 and pi over... And what a nice place for me to choose. Okay. Yep, unit circle. So basically wherever I see a y, I'm going to put that, right? And we'll just have this one diverge over here. And wherever I see an x, I'm going to put, well, let's face it, the same thing. Why did I say I chose such a nice place? Pi over 4, it's on the unit circle. And on top of that, it's right here, right? Yeah, basically at pi over 4, what are sine and cosine? They're both square root of 2 over 2 and, right? And which one's cosine again, technically? The first one, sine's the second one. And so this one right here says cosine of pi over 4, which is, excuse me, square root of 2 over 2. This one I just put a rectangle around is cosine of pi over 4, which is square root of 2 over 2. All over. Sine of x, square root of 2 over 2. And sine of y, square root of 2 over 2. So in other words, all of this work to get 1. Yes. No, because there was a negative on the sinus as well. The negatives cancel. Nice. Now, if I were you, I would have possibly made one slight alteration at the end, but how could you rewrite your derivative? But again, I have better knowledge of some of the trig. You know, I know what they are. Yeah. Close. Cotangent. Cosine of y over sine of y is cotangent of y. Cosine of x over sine of x is cotangent of x. But I stayed with those because I know that we have a better knowledge of sines and cosines. But you could have written this as cotangent of x, cotangent of y. It's the same thing. I don't think you necessarily know the cotangent values at pi over 4. So that's why I stuck with sine and cosine. Yeah, it is. You would have gotten 1 times 1, which is 1. Yeah. But I just figure you're much more comfortable with sines and cosines because of the unit circle. So, any questions?